Great. So welcome. I'm here from the University of Leoben, and I'm going to present some of the coolest research topics that we're working here today. It's going to be about sustainable hydrogen and carbon supply, and also about energy mining. And to start with, let me introduce myself. My name is Robert Oben aus Emler, and I'm from the Methane Universität Leoben, from the Resource Innovation Center, where we work at some really cool topics related to the raw materials industry. I will try to do this rather quickly in about 15 to 20 minutes, and if necessary or if you want, we can have a little discussion later on. I will be available. So let's start. I said hydrogen, so let's look at hydrogen first. Hydrogen is one of the elements, of course, and I put the periodic table of elements here on the screen. And hydrogen is there on the top left corner. It is therefore the lightest element that we have, that we know. It is most abundant element in the universe, so almost everything is made of hydrogen. Only a tiny little bit is not hydrogen. It is the major constituent of our sun, where it is roughly at the moment around 75% of all the mass in the sun is hydrogen. The rest has been converted to helium by fusion, and that's also a really cool process because it produces energy, and this energy we can see as light. And that's the main reason why we're here today, why you are online and I'm online, and why we all live as animals and human beings, I wanted to say, here on the Earth. So it's on the Earth also available, hydrogen, but it's only in the crust, mainly in the crust only. And here an overall share of around 2.9% can be attributed to hydrogen. Here at the Earth, at the crust, we have it found mostly in compounds. So not in its pure form, in just compounds. And the most well-known is, of course, water. You all know that. There's water everywhere around you, probably. You're drinking it, I'm drinking it. There's also seawater, so a lot of hydrogen is in water. There's other substances that contain hydrogen, which is, for example, oil and gas, which contain a lot of hydrogen. And then, of course, a lot of hydrogen is also found in various minerals. So hydrogen is not found in its pure form normally, where it would be a color and odorless gas, H2, just two molecules of hydrogen bond together. But that's actually the one that we are after, because that one is also an energy source, and it has around a calorific value of around 33 kilowatt hours per kilogram. So to compare that with, for example, natural gas, this is 3 times as much as natural gas. So today, we are even using hydrogen, and we're producing it. So I've put here some numbers of rough numbers, partly estimated for the projection of current year 2020. So overall, globally, we produce roughly 120 million tons of hydrogen per year. In the European Union, 12 to 13 million tons. And well, we are from Austria here. So in Austria, roughly 1.5 million tons. That is not much, but it's still significant. So let's have a look what we really use it for at the moment. And we use it for these 4 main things. It is the production of fertilizers, so here mainly ammonia. It's hydrotreating of petrol, so to produce the fuels that you need to drive your cars, we need hydrogen. We also use it for the production of methanol and also partly for some metallurgical processes. As you see here in the bottom right on this graph, most of the hydrogen is used for ammonia. So this is the dark red color. The next most part is used for the hydrotreating in the petroleum industry, and then a bit of the others. So let's have a look on how we can produce hydrogen. 40% of this overall amount of hydrogen that we produce is actually a byproduct of other industrial processes. And this hydrogen is not available because it's being used there directly within the process. So, for example, it will be used to be converted to energy that fuels basically the process itself. The other 60% are the ones that we really directly produce. That's the one hydrogen we are after, that we want to use for those applications. And there is a main production process for hydrogen production currently, and that is steam methane reforming. And steam methane reforming relies mostly on fossil fuels. So here in this graph, you can see that there is the main source for steam methane reforming for hydrogen production, gas, natural gas, then second next oil and coal, and only this gray little part there that you see, that is electrical energy that is being used for the production of hydrogen. So in total, 95% of the hydrogen production relies really on fossil fuels. And that's what it looks like. That is a picture of a plant for steam methane reforming. So that's a big plant, a big process. And what it does inside, I don't want to get too chemical and too technical here, but it takes, for example, the natural gas, and with water, it will be converted to hydrogen and CO2. And I already put the CO2 there in red because CO2 is obviously something we don't really want to have right now anymore, not for most processes. We want to reduce the CO2 emissions. So that is probably not the best process when thinking about our climate and climate change that is mostly attributable to the emission of CO2. Well, and if you add it up and if you do the maths, then you will find out that around 12 kilograms of CO2 are emitted for each kilogram of hydrogen that you produce here by steam methane reforming. So let's go ahead. Sorry. So you have heard about hydrogen a lot, I think, and you have picked up that there might be applications here and something to do there. And let's have a look at the hype. Why would it be so important to have hydrogen? What are actually applications that are of interest? Well, I said it's an energy source. So it has a high calorific value, and that, of course, can be used to produce heat and also heat industrial processes, houses, anything you can think of. That would be one major application. Another one would be that you can use it in the industry as a reduction agent to produce steel, for example. Steel is one of the main emitters of CO2 at the moment. You can also use it, hydrogen, to capture CO2 from other processes. Here is an example of a cement plant. So I was talking about capturing CO2. And here's an example of cement. Cement produces around 1 ton of CO2, maybe a little bit less per ton of cement. And most of that CO2, more than half of that, is not from fossil fuels. It's not from bringing the energy to the process. It is from the raw material. It is from limestone. And that we can't get rid of, right? Even though we could heat and produce cement without fossil fuels, still the CO2 of the raw material limestone will be emitted. And hydrogen can capture that and produce something cool out of it. For example, it can do synthetic fuels. And synthetic fuels, are something we will need still in the future. Here's an example of an airplane. Airplanes will not be able to fly on battery power or not even hydrogen power probably. It will need synthetic fuels really to be still in operation. I mentioned mobility already, and hydrogen can play a major role in mobility, especially for heavy vehicles, for trucks, and intercontinental traffic of big and heavy loads. Also, hydrogen can be converted back to electrical energy, and that can be used for everything else. So if you use electric energy to produce hydrogen and then convert it back to energy, that will be then like the battery for electricity. It will be hydrogen to store electrical energy in another form. So that's a lot of cool applications. But what will be the demand I mean, a lot of people think about where to use it and what to do with it. And here is a little forecast of how much that could be. So at the moment, this is what we're using, around 8 to 10 petajoules. This is now energy, but that's the amount I mentioned before. It will increase tenfold roughly until 2050. So a lot of more hydrogen will be needed. And obviously we cannot produce it by steam methane reforming, because we are really producing a lot of CO2 with it. So how could we possibly produce it? And I'm sure that you remember from the beginning that hydrogen comes also in the form of water, liquid H2O. And that can be split into its components, hydrogen and oxygen. And actually that process is called electrolysis. I think most of you have seen this somewhere in a school experiment or have done it by themselves. It's pretty simple and it does the job. However, to do it, because hydrogen in the form of water has such a strong bond, it needs around 50 kilowatt hours per kilogram of hydrogen to produce that reaction or to facilitate that reaction. And depending on where this electrical energy comes from, that can have a major contribution to CO2 emissions. So that could be something around 30 kilograms of CO2 per kilogram of hydrogen if you take the power directly from the next coal power plant. It could be low if you really go to renewable energy. So that means in the end you need renewable energy for electrolysis, otherwise you will just produce a lot of CO2 again for producing your hydrogen, which is not what we want. But let's have a look here. Well, what can we do? I said it's an energy source. So if you take oxygen and you burn it, you get gaseous hydrogen. And of course, this reaction is exothermic, so it produces energy of around, we said that before, 33 kilowatt hours per kilogram of hydrogen. And that reaction does not produce any CO2 whatsoever, of course. It's just H2O pure form. You can see two things here, that number one, the energy that you get of burning the hydrogen is obviously less than the energy you use to produce it out of water. And also, if you look at it really, if you need CO2 to produce your hydrogen, even though the reaction to water again is CO2 free, you actually still produced CO2 to produce that energy. So the 0 kilograms per kilogram of hydrogen is just for the combustion, but not including the production or the transport or the storage or anything else around. Let's bring that to other numbers. So I said in 2020 we had around 120 million tons of hydrogen produced. That would mean around 6,000 terawatt hours of electric power that we need to produce it. For Austrian demand, that would be less. It would just be 7.5 terawatt hours, but that's still a lot. Let's have a look at how much energy in Austria we really need every year. And you see that here in that graph. The red line on top gives you the total electric power that we need in Austria, or that we produce in Austria and then also need. And in 2018, I have the number here, the recent one, is around 74 terawatt hours of electrical energy that we need. Compare now the 7.5 terawatt hours that we would need for hydrogen production, then it would actually be around the amount of electric power that we generate by wind power plants. So that would be the light blue color. In Austria, we're lucky, we're producing a lot of renewable energy already. So 60% or 65% are renewable energy. But we would need that 7.5 terawatt hours right now, additionally to what we see here. What about looking in the future? What about 2050, when we need 10 times as much hydrogen? We would need actually 75 terawatt hours of hydrogen, of electric power, to produce the hydrogen. And that would be almost exactly the amount of energy that we need right now, the whole nation in a year, without even producing a single bit of hydrogen by electrolysis, or just almost no. Anyway, that means actually we would need so much more renewable energy installed until 2050 so that we can double our energy consumption. And that's quite a lot of energy that we need, and that's quite a lot of money and quite a lot of infrastructure. And the question is that possible to do? Well, I don't have the answer right now. We can come back in 30 years and check. But is there anything else that we could do? Is there another source? Well, if you remember from the beginning, it was water, and then we had also the fossil fuels. And if you just look at methane, CH4, so natural gas, then you could actually also convert natural gas into hydrogen and carbon. This process is called pyrolysis. And it only needs around 1/4 of the energy per kilogram of hydrogen than the electrolysis. So that's a big benefit. Also, again, if you use renewable energies for that, you will end up roughly with 4 to 6 kilograms of CO2 for each kilogram of hydrogen that you produce. And additionally, you get carbon, solid carbon, no CO2, nothing like that, solid carbon. And solid carbon is also a very important element that we need already now a lot for batteries, for example, and other things, but also for many more applications possible for the future. And so I think we better look at that now. But before, let's check the figures again. If we produce 120 million tons of hydrogen a year, and we would do this only by pyrolysis from methane, we would end up with around 360 million tons of carbon. Well, that's quite a bit, and we will see in a bit that this is a lot. So to compare it, let's have a look at what carbon is used for today. So here's a picture of graphite, which is also called the black gold. And it's got some applications, of course, already that you all are familiar with, or most of them, I think. Well, if you drive a car, your car has tires, and tires need carbon. Also, other rubber products need carbon, of course. It's used in electrodes and batteries. So to produce steel in a steel plant, in an electric steel plant, you need electrodes that are made of graphite. You need graphite for the batteries, also for your electrical cars if you have any. Then we need it a lot in refractories. And refractories you need to make almost everything that you see around you. Every metal that needs to be molten, everything that needs to be heated to high temperatures needs refractories in order to make it possible to be produced. And most of those refractories also include at least some content of carbon. Another cool thing is graphene. Graphene is just one layer of graphite. So graphite has this layered structure, as you can see here in the picture, but many of them on top of one another. And graphene is just one layer. So it's a two-dimensional substance, a material that has the highest strength that we know, that has a lot of other cool properties. And unfortunately, at the moment, it's not available to great extent, but it has a high potential because it can be, for example, used in electronics. It can be used in all kinds of building materials, probably, and many, many applications more. Today, we still do this. We already do this, but only to a small extent. So what's the world market of carbon today? Well, it is around 15 million tons. So compared to the 360 million tons that we would produce already now, that means we are done after like 2 weeks of the year with reducing our carbon for the rest of the year. That means, of course, we need to look further. We need to look for other applications. And in order to do so, we need to relocate ourselves a little bit back in time, maybe 2,000 years, and also a bit on the other side of the globe, so here on the back side, into the Amazon Delta. And there is something really cool that you can find there, and that's Terrapreta, which is a soil that has been engineered by the people that live there. And that Terrapreta contains biochar, which is just a pyrolysis product, remaining product of carbon from biomass. And if you look closer at this, so here is an enlarged micrograph picture that shows you the structure. You see honeycomb kind structure in there. That has really cool properties because it can store really efficiently the water and nutrient that the plants later on need, and it can distribute this water and nutrient to the plants whenever they need it, so the soils don't dry out. Also, this structure is a perfect habitat for microorganisms, which in return helps you to generate more humus in your soil. And on this picture there, you see a man standing on a topsoil layer, and this topsoil layer you see is darkish to around the depth of 1 meter. Underneath it, it's rather brownish. That soil was done around 2,000 years ago by just adding biochar into the soil that was available there, and it is still there, and it is a really fertile soil that helps people grow all the crop and food that they need there. You can also use it as an animal feed. It will help your animals to stay healthy, and it will be really beneficial also for the living of the animals themselves. You can use it also as an additive to composting to reduce the emissions of the composting itself, so reduce CH4 and nitrogen emissions of the composting. You can also put it in a cropland, and really to quite a high amount. You can use like 50 tons per hectare, and it will just increase the amount of crop and food that you produce. And it will stay there, and it helps you to keep your plants or to keep water there and nutrition there for your plants, and so that they can use it whenever they really need that stuff to grow. There's one problem: if you use biochar as it's produced right now, and it is produced, then it's quite expensive. So if you're lucky, you get it for €1,000 per ton. Or even €1,500 per ton, but that's quite expensive. Nobody can afford, not one farmer can afford to put even 1 ton on 1 hectare of cropland. Well, there is a solution, and that is due to the carbon that we produce from the pyrolysis. Here's a micrograph of that. It is looking differently, but again, similar to the biochar picture there, you see a really high surface area, and that surface area is the crucial property. Additionally, we are looking here at the university at different pyrolysis technologies that try to tinker the properties really of that carbon product, so that in the end it will be able to use it for all of these applications, or even more applications that I didn't show you today. So in the end, really, that is a big benefit of pyrolysis, not only being able to supply hydrogen to a good extent with low energy demand compared to electrolysis, but also additionally have carbon as a potential resource for really cool applications. A Chinese proverb says, when you drink water, and think of the source. I hope after what I showed you today, the next time you use hydrogen, you might think of the source. So my name is Robert Obernaus-Emmler, and I'm from the University of Leoben. And I would really like to thank you that you followed my talk. Well, if there's no question right now, then let me remind you again that we have in the chat a link to a document. If you fill in your name and all the other information that are required there, you can get a certificate that you have participated in this course. And if you have any other question later on, you can always come back to us and ask your questions there if you want. Additionally, if that might have been too much of information at one go and you would like to have a look at it again, I can also refer to our YouTube channel. So this is just on YouTube. If you enter Montana Universität Leoben, RIC Leoben, you will find a video series that was prepared by some pupils in a project that we made, and that is available in German and English, and it will give you a lot more information, a lot more details, funny, nice pictures and animations about hydrogen, about carbon and their use, and also about pyrolysis, of course, and electrolysis. And I think it's a good summary in case you would still need some further information on that. Thanks again for participating, and the weekend is ahead, so I wish you a great weekend. If you happen to have snow, go enjoy it. If not, also enjoy your weekend and be safe, and all the best to all of you. Bye-bye and Glück auf, as we say from Leoben, Austria.